Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Finland, and I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the fun things happening inside the universe. They're great topics. I love studying the universe and trying to figure out what is going on out there, and I love chatting to everyone about all of the cool things that I get to study. So that is what we're doing here on Cup of Cosmology. And as a reminder to anyone who's new to the show, this is an interactive stream. You can ask me anything you want and we will try to answer. Hey, David Dunn in first. Great to see you in the comments here, as always. Because cosmology is a broad topic and there's a lot of stuff we can talk about, I'm not going to be doing this alone today. So I have a guest with me and I'm going to bring them up on screen so they can introduce themselves. And you are now on screen. Hi, David. Welcome to Cup of Cosmology.
So I'm David. I'm an associate professor of gravitational wave cosmology here in the University of Helsinki, and I use large-scale computer simulations to understand what happened right at the very early first few picoseconds or the very first instance of the history of the universe. And I work with Diana.
Fun thing, working with me. So, yeah, you mentioned a lot of cool things there, gravitational waves, early universe, big computer simulations, all fun topics. So can we elaborate a bit on this maybe? Why do we need simulations for the early universe? What do they tell us? How is this connected to gravitational waves? Can we get a summary of your work?
The equations are hard. I can't use equations to save myself. Computers are easy. So I work with computers, and also the computers are, yes, I can just play with computers until they work. I can't play with equations until they work. I haven't got the patience for that. That's my reason for that. But the more prosaic reason why we need simulations is that a lot of the physics of the early universe is very complicated and kind of difficult to understand as kind of like small tweaks on things we already understand, is what we'd either describe as non-perturbative or very sensitive to initial conditions. And that means that simulations are needed to kind of predict what would actually have taken place, whether it be kind of understanding the way in which a particular scenario would play out, or else just playing, like simulating what actually happened, or playing out through the kind of history of the universe, like the timeline. Both of these things need us to actually use simulations, just because the equations are too difficult to kind of do by hand, and which is good for me because I'm bad at doing equations at the best of times, but I'm relatively good at doing things on computer. So that's why I ended up where I am.
Yeah, I like that, and I like your answer to that, because my answer to why we need simulations always is like, if the computer can do physics for me, I don't have to. So if we can throw things at a computer, it makes our life easier. And as David Dunn is saying here in the comments, if you haven't done so already, please like this video, leave a comment, subscribe, do all the usual YouTube stuff. It helps us build an audience. And I hate saying that, but please just press all of the relevant buttons on YouTube and make stuff happen. So last week, I was talking about gravitational waves on this show, and I was focusing specifically on the LIGO and Virgo gravitational waves, so the ones that we have actually been able to measure, black holes smashing together. But you mentioned that we simulate gravitational waves in the first picosecond of the universe. So just to give people an idea, can you tell us if these are the same type of gravitational waves? Are they also ones that LIGO could measure? What's the difference between these early universe gravitational waves and the ones we've actually measured?
Well, a gravitational wave is a gravitational wave. It doesn't really matter what wavelength it's at. It still does the same thing. It's still a wibbly-wobbly thing on the rubber matter space-time. But the reason why this is a bit different, and what I look at, is kind of using gravitational waves as a way to see behind, like into the opaque early stages of the universe. When we look back behind the stars, like to the very furthest reaches of the universe, like back to when that we can see, so the cosmic microwave background, which is the earliest photons that we see coming towards us, that's as far back as we can go. But if we want to see if we want to be bystanders and observe what happened kind of before that, then we can't use photons for that. We can't use the light from the CMB. The CMB is kind of just it's a echo of what happened in terms of visible light about 380,000 years after the universe got started, which either feels like a very long time or a very short time, depending on your idea of timescales. But for me, it feels like both a very long time and a very short time. But it's far too long to look at the things I want to look at. So if by the time 380,000 years have elapsed, all the cool stuff I want to know about is all diluted and mashed up into other stuff, and you can't work out what's going on. So I need to see what's happening. If I need to, I mean, I want to. I don't need to. I'll survive without it. But I want to see what's happened, these few picoseconds after the Big Bang, because that would tell us a lot about, for example, what lies beyond the Higgs boson. So the kind of the stuff which, if we have the standard model of particle physics and we add extra stuff to it to solve some of the problems we have, and I can tell you about some of the problems. I've got huge problems with the standard model, but I can tell you about some of the problems that we all have with the standard model and why we need to fix it. And we're not necessarily going to be able to probe everything that we might want to with new particle accelerators or dark matter searches. And so looking for echoes of the physics that they might have been up to, they might have got up to, those extra particles or new phenomena might have got up to right after the Big Bang is a useful reason for looking for gravitational waves, because, as I said, they're a probe of what happened long before this 380,000-year-old photon light source came on. So yeah, that's why we need gravitational waves. Well, we don't need them, but I'd like to see them. That's why gravitational waves are important to me, because they let me probe what happened right after the Big Bang, long before this microwave background of photons was made.
Just want to make a comment here that we are less than 7 minutes into the stream and the CMB has already been mentioned, and it wasn't my doing this time. There's an ongoing joke that with my followers that I'm incapable of spending more than 5 minutes without mentioning the CMB, and it was not my doing. But yes, the early universe gravitational waves let us see even further back in time than the cosmic microwave background radiation, which is pretty cool. And I've often referred to the CMB as like the oldest light we can see in the universe. But now we're talking about going even further back. And of course, for this, we can't use light. We need gravitational waves. And I also just want to comment on what you said about 380,000 years being both a short time and a long time. So when I was working on CMB physics, I always described it as I'm working on early universe physics. And for me, 380,000 years was early universe physics. And now we're looking at stuff that is the first picoseconds. And it's like I can no longer refer to the CMB as early universe physics. That sounds like late times.
Yeah, we talk about in astrophysics and cosmology, we think about foreground, so things that are in front of other things. And to me, like everything that happens like that late is a foreground. It's stuff which gets in the way of the cool stuff.
Yeah, I'm not going to accept that the CMB is a foreground. That doesn't work for me. We have a question here from James asking, how can we differentiate between the gravitational wave from the beginning of the universe, or these ones in the first picoseconds, and the ones, for an example, of two black holes colliding, such as the ones LIGO have seen? So what is the key difference? You mentioned already the word wavelength. You just want to elaborate on that?
Yeah, so that's a good question, James. Thank you for your question. So firstly, we think there'll be black holes of all shapes and sizes colliding. So the ones we've seen at LIGO are just one kind of black hole merger pair that we'll probably see once we have gravitational wave observatories and missions stretching into other wavelengths. Like the LISA mission is space-based gravitational wave mission that I'm involved with. We'll see probably the merger of supermassive black holes in very distant galaxies. But regardless of how big the black holes are, when they merge, they're localized. They're happening at some point in space and time, somewhere in the universe. And when we detect it, we already, with the observatories we have, LIGO, Virgo, and Kagra, we can kind of localize with, these are not very accurate. They're not like a telescope. These gravitational wave detectors, you can't just they don't tell you like, oh, it's over there. But they're kind of more like the aerial on an old TV set, that they're more sensitive to one direction than another, which is why, like, if like me, you remember tuning in analog TVs, you got better reception when you pointed one direction than another direction. So you have to tune in your, basically how strong it looks, the signal looks in different detectors tells you where it comes from. So these black holes that you see those are kind of they happen at one single point in space and time, and that's why when LIGO records them, it sees these like chirps that you see kind of going up as the frequency goes up as they spiral in towards each other, and then it disappears from the signal. Whereas the gravitational waves from the early universe, they come from all around us. I mean, they hopefully be, if not exactly isotropic, then should be pretty close to being that. So like, no matter what direction you look in, you'll see the same thing. So one thing we can say is that it happens at a particular point in time. So therefore, it's not that's the black holes merge and then they're merged and they're done, and it doesn't happen again for that particular pair of black holes. And the other thing is that, like I said, these black hole missions, these gravitational wave missions are a bit like they're basically observatories, and they have some directional sensitivity, a bit like an old TV aerial, and therefore we can work out roughly where they came from. Neither of those things are true for early universe background, if that makes sense. I think that's the answer I'd give.
So going on that, when we talk about these early universe gravitational waves, just repeating what you already said here, we are not really looking at point sources of coming from a specific point, but we would actually, if we could measure these someday, we would measure a background of gravitational waves kind of uniformly distributed. Like we have the cosmic microwave background radiation, we could have a gravitational wave background producing the first picoseconds, which is incredible when you think about just how much that could tell us about the early universe. It's very cool to think about it. So you mentioned LISA, and of course, LISA is a great mission. So can you talk a bit more about LISA? Just tell us what it is, why we should care about LISA.
So LISA is when we're on Earth. If you've tried, I don't know if you've ever tried to build a giant laser on Earth, but I haven't either.
I have not.
I've spoken to some people who have, and it's difficult to build a laser cavity more than about 4 kilometers long, just because the Earth is big, but it's also not that big. Things are both big and small, and 4 kilometers is already getting to the point where the curvature of the Earth becomes a thing. And if you want everything to be in alignment, it starts to kind of deal with the seismic noise becomes an issue. So, for example, if you have a truck driving past, it can send things out of alignment. So you start to deal with background noise, like vibrational noise, seismic noise, dealing with the fact that, yes, you're trying to build a straight thing on a surface which is curved. And all these things kind of restrict the size of these gravitational wave detectors on the Earth to a few kilometers in length, which also gives a certain kind of limit to the frequencies they can pick up, which are about 100 hertz or so is the peak sensitivity range for LIGO. Sorry. So if we want to go to longer wavelengths, one of the ways to do that would be to go into space. So there's several proposed ways of doing this, but the one which is most advanced and which now is kind of under preparation, so there's actual people planning this and designing it, and contracts are being signed and money's changing hands, is the LISA mission, which stands for Laser Interferometer Space Antenna. It's not a recursive acronym, sadly. The first does stand for laser, not LISA. The Laser Interferometer Space Antenna. And it's going to be 3 spacecraft, and they're all going to shoot lasers at each other. And they're going to be sent, there's a nice visualization by Anna. I think Anna was on your show a few weeks ago, if I'm not mistaken, Diana.
A few months ago by now, but yes.
Time flies. It's a short or a long time. Everything's short or long, depending on how you look at it. And these 3 spacecraft are shooting lasers at each other, and they're going to be about 10 to 15 degrees behind the Earth. The Chinese have a competing or complementary mission called, I think it's Tianqin is that one, and that one will be about 10 to 15 degrees in front of the Earth, which is no bad thing. The two is better than 1, so it's not a bad thing that they also have their own plans. But what these will do is these 3 spacecraft will orbit in this kind of cartwheel, as you can see these spacecraft doing now. They're doing these cartwheels around the sun, and then they're about 2.5 million kilometers apart. But they're not strictly held in place between each other. They try their best to stay 2.5 million kilometers away from each other, but we can't force them to be that far apart. They're going to drift a little bit over time, and that's fine. 2.5 million kilometers is about 8 times the Earth to the Moon distance. So if anyone asks you what's the largest object that's humanity is going to construct, then you could argue it's this triangle of 3 spacecraft, because it's it's an object with a side length of 2.5 million kilometers. So we're almost getting to kind of Arthur C. Clarke levels of design here. But in any case, these three spacecraft will send lasers to each other, and the lasers will have a little coded signal inside them, which, like the modulation of the laser signal, which will basically allow the spacecraft to work out how much time has lapsed between the laser leaving one spacecraft and arriving at the other one, and then they'll basically send that information back to the first spacecraft. And with all the combinations of these timing information between the three spacecraft, you can actually build up interferometer, which tells you basically how far apart the spacecraft are at any one time. And from that, you can tell if the distance between the spacecraft has changed, and that itself then tells you if a gravitational wave has changed, because as I think I alluded to, and perhaps people have heard before, the gravitational waves are like ripples in space-time. So actually the way you experience them is by the length between two objects changing. And I have it's like this ruler I have here changed in length. I have all the props I need here. If this ruler were, the ruler would no longer be 50 centimeters long. It would be longer, but you'd of course have to have an external reference to measure it by. So that's what gravitational wave missions are, basically missions which measure lengths very accurately as a function of time, over time. And LISA is going to do that, but over 2.5 million kilometers, which then means that the frequencies it's sensitive to are quite low. So it's about millihertz rather than tens of hertz or hundreds of hertz, like for stuff you can do on Earth.
I was going to make a comment about LISA, but now I need to make a comment first. I'm wondering if we can find a way to get you to use the fluffy dragon behind you as a prop.
This is Kali. So Kali is the mascot of Ramsau am Dachstein. I think it's Ramsau am Dachstein, the cross-country skiing area in Austria. And I have no idea why I got it, but I did. So this is Kali.
Nice, I like Kali. Okay, before getting distracted there, I was going to just add a comment of how incredible the design here is, because we're talking about really sending 3 spacecrafts chasing the Earth, and they're going to bounce lasers back and forth to measure something that happened in the first picosecond of the universe. Now, this sounds like it's right out of a sci-fi book, and somehow this is something that we're building. We know it's going to work because there was already the LISA Pathfinder mission, which was a small-scale one, just to prove that the technology is actually viable, that we can measure these lasers with enough precision, that we can build this.
Yeah.
The expected launch date is currently like 10 years from now.
I don't think this is where I put my bureaucrat and like awkward political hat on to say I don't think we want to give launch dates. Yeah, it'll be ready when it's ready, but it's going to be sooner than you think.
Not soon enough.
I mean, you can't. Yeah,
you can't rush these things.
If you rush it, then it'll go wrong. Like we wouldn't want that to happen. You have to do these things. You have to work.
Yeah, let's get it working first, but still, the sooner the better. I'm just impatient to see what we're going to measure. So we do have a nice question here. We were talking about background. So Anne just asked, what would the gravitational wave background look like? And I think that's a great question, because we can't actually see gravitational waves directly, because there are ripples in space-time. They make things bigger and shorter in one direction. So we couldn't really see them. You wouldn't end up with a pretty CMB-style map of gravitational waves. But we know that we can map gravitational waves kind of into sound. We've seen this for the LIGO-Virgo ones. So you might all have heard by now the chirps associated to the colliding black holes. So now a question for you that I know you've been asked before. What noise would the gravitational wave background make?
Well, it depends on what. It probably wouldn't be very interesting. I think I can't answer that. It would probably just be a horrible hiss, to be honest.
Yeah.
I mean, the cosmic microwave background, as I think many people remember, was discovered by it's basically the hiss between radio stations, right? So it was discovered by mistake at a microwave, like a microwave antenna, which was being used for testing in Cambridge, I think, in the 1950s or something. Do you remember the story? Radio telescope. But anyways, basically, it sounds like the noise between stations. Everything about me today is an analog TV set, so like it's noise between channels. Like it'll be stochastic. It'll be very it will have it'll just sound like noise. The exact spectrum of the noise will probably be difficult for the human ear to hear. But yes, I think
If
that's very hard to answer.
Yeah,
Maybe like a hint.
if anything, would just be like a low rumble. I think like you probably wouldn't even notice it. I did hear someone once say that it would make a sound similar to when you can see northern lights, and as I've never heard that, that doesn't help me. But apparently, you could just imagine like this low background rumble. So I
Yeah,
think that's cool to think about.
of course, it depends on what you do, right? Because if we're going to say I mean, I'm very happy if we don't see anything at LISA because that also rules out a lot of stuff. But like if you see something at LISA, which is from cosmology, so it's from the very early universe, that's like a millihertz. So I don't think there's any ears on Earth except maybe some like evil space sea monster, which is very huge, whose ears can pick up 1 millihertz. That's quite a long time. That's 1,000 seconds. So yeah, that need like eardrums like a kilometer long or something like that. So I think yeah, if it's like something at a higher frequency than that, and maybe like 100 hertz is almost in the range of human hearing. I think it is in the range of human hearing. I think, but yeah, I think so, anything at least that would be kind of we're talking blue whale level eardrums, if not bigger.
Well, maybe the blue whales can hear it for us.
Hmm.
So you made a really interesting comment there that if LISA doesn't measure anything, that would also rule out a lot of things. So I want to go down that path. What would happen if we build this amazing, expensive spacecraft, ended up there, it measures nothing? Does this mean we failed, or what does this tell us?
Well, I mean, I'm like a bottom feeder, right? So I'm a cosmological bottom feeder. So basically, there's a lot of almost guaranteed stuff that Lisa will see. So Lisa is right in the right. There's within the Milky Way at least there's many tens of thousands, of hundreds of thousands of white dwarfs and other small stars orbiting other small stars, which is a really good source of gravitational waves at basically one frequency. So the two stars orbiting each other, if they're not like, so we were talking about black holes a moment ago where they spiral in towards each other and the frequency goes up like this kind of thing. If it's just two happily, quietly sitting there, white dwarfs or something, doing their thing, going around each other, not really getting any closer. Of course, they're going to emit some gravitational radiation, but they're not getting too much closer too quickly. They're just going to sit there happily doing their thing, and they're going to emit some gravitational waves at a certain specified frequency. And in fact, the existence of these white dwarfs is important to LISA because we're going to use several of them, which we can observe directly with optical telescopes. We know their period and we know where they are. And we're going to use them to calibrate LISA in the first place, so we know it is working and what it's seeing. So these are called so-called verification binaries in the LISA jargon. So actually, these are guaranteed because we know they exist. We can see white dwarfs orbiting other white dwarfs and other small compact objects in the Milky Way. I mean, also know from textbooks that they produce gravitational waves that are very close to a single frequency. It's almost like a kind of a single note in a piano or something. And there's going to be lots of those. So there'll be a cacophony of these compact binaries. There's going to be, we know supermassive black holes tend to merge in very big galaxies very far away. So we also expect to see them, and they'll be like very low frequency. These will be like the blue whale frequency chirps. So they'll be like the same chirps that you see with LIGO, so the vroom thing, but happening at millihertz scales over like years rather than seconds. So we'll see those as well. And there'll be other things as well. So these things called extreme mass ratio inspirals, where very small things spiral into very big black holes. And that's why it's called an extreme mass ratio inspiral, because it's something which has a very small mass falling into something which has a very big mass in a spiral shape, I guess, inwards, so in spiral. So there's all these things which basically are guaranteed, which our dear astrophysicist friends think are exciting. And then they all very skeptically think, well, sure, you think you can see something from the early universe. And I'm like, I mean, as a treater, I'd like to see something from the early universe, but I'm also very happy if I don't see something. Because if you turn LISA on and you wait a couple of years and you don't see anything, that already says that there's lots of people's pet theories, like particle physics phenomenologists' favorite pet theories of what happened in the early universe can be ruled out by that. Just like when LIGO saw to neutron stars merging, and then we saw a gamma ray burst a little bit after that. That told us basically how long the gravitational waves took to get to us compared to how long the gamma rays took to get to us. And that then tells you how close the propagation speed of gravitational waves has to be to the propagation speed of light. And it turns out that gravitational waves pretty much travel at the speed of light, which is disappointing for people who want to play around with theories of gravity, which are not that close to general relativity, because many modified theories of gravity predict a velocity of gravitational wave propagation, which is different from that of light, which didn't happen. So even not seeing something falsifies lots of theories, and that's a good thing. So I'm not the sort of person who's like, well, if I don't see something, then I'm sad. I'm very happy if I see something. Or not something. If I'm very happy if I don't see something. Yeah. No,
Yeah, I think either way, if we see something, then we need to figure out what we're seeing. If we don't see something, we need to figure out why. But I do want to ask a potentially provocative question with what you were just saying. So we have all of these astrophysical things that the astrophysicists care about. Behind all of this, we have the stochastic gravitational wave background, we hope, or potentially, maybe. Will we actually ever be able to disentangle this stochastic gravitational wave background from all of the astrophysics?
hopefully.
Is it realistic?
I think the better if there is a very strong stochastic background, I mean, it doesn't, then of course that'll be kind of the first thing you see, and that actually might be bad, because if you can't calibrate Lisa with these verification binaries that I mentioned, then we're in trouble if it swamps out everything else. But I suspect that's not going to be the case. There's various things I think are likely, and Diana, you and I are working together on trying to extract whether we can, how quiet the cosmological background has to be in order to see it or not, or before it becomes kind of merges into the noise. So we're already trying to figure that out. You and I and tens of other people around the world. But yes, it's a good question. Like I said, if you turn it on, you see something immediately, then that's itself interesting. And if you turn it on, all you see after a few years of taking data are white dwarf binaries, supermassive black holes, the kind of the menagerie of kind of boring astrophysical objects. Then you probably start to say to yourself, okay, maybe it's not what we thought. But disentangling one from the other is definitely a thing we can do. It's just it's a good question.
Yeah, I asked that question knowing full well that we're working on exactly that, but then gives us a chance to plug our work. And I do think it's an important thing to address, because we have all of these other sources, so it's always interesting to know how much we can actually take this background out, or this foreground, depending on your perspective. Yeah. And the other side of it, as you said, we don't yet have a clearly defined launch date, so we have plenty of years to get ready to make sure we can extract this background once we have data. Yeah,
there was it David Dunn mentioned 2037? So yeah, I mean, it could be earlier. There's stuff happening behind the scenes, which means it might be earlier, but I really can't go into detail about that. And like I said, with my politician's hat on, I don't want to say more than that. 2037 is definitely if you want to have a number, 2037 is a very nice number.
It's as good as any other number we can give. So going back to some questions here from the chat, because we've been ignoring them for a bit. We have a question here from Ben of why hasn't the radiation from the early universe moved past Earth? And related, is there any information from the early universe that is lost forever? So again, I think this is more like CMB physics related, and this is a cool question. Other side, I think. Yes, anyway, my problem. The cosmic microwave background radiation is constantly moving away from us. Well, I'm sorry, not moving away from us. It's constantly being redshifted. It's gradually changing the frequency. But you have to imagine that this is everywhere in the universe, in every direction you look. So it's not really being sent towards the Earth. It's just coming from every direction towards wherever you are. So if you were on a planet a couple of billion light years away, you would still see a CMB. A very different looking CMB, but it would still have the same statistical properties, we think. So it's not going to go past us at any point, but it is gradually moving to lower frequencies, which means eventually it will move beyond the microwave range and into radio range. And then you can ask the very interesting question that I got asked last week in the office, and which I haven't yet calculated the answer to, of was there a time when the CMB was actually in the visible part of the electromagnetic spectrum? And the answer is yes. And then the follow-up question was, what time or how long ago was that? And I said that's, left as a calculation to be done at future times.
But probably quite early on.
Quite early on. I think probably not long after it was formed. Like I would say definitely before the Earth was around.
But I think one thing to think about when it comes to this idea that whether the cosmic microwave, the word background in cosmic microwave background is a kind of a misnomer, right? Because it's not like a sunset you're watching kind of off in the distance. It's actually happening here. Like the stuff you're made of sitting right here and now was, is making the CMB for people over, those, billions and billions of light years away or whatever. There's nothing particularly backgroundy about it. It's everywhere. Is that a fair thing to say?
Yeah, I think so. I mean, it's background in the sense that it's the background wherever you look, but it's not a faraway event. It's something that is indeed happening now, which is kind of fun to think about it, and still it's confusing to think about. And then for the second part of the question of, is there any information from the early universe that is lost forever? I think that's a really interesting question. And there are parts of the universe that we haven't yet been able to observe. Parts of the universe, I mean, like parts of the history of the universe. There's a whole period in the history of the universe that we just call the Dark Ages, because there's not much happening there. There's no real lights that we can see. So we can't make many observations there. We are trying to push it with like radio astronomy. But the cool thing is gravitational waves will see through this. So we can use gravitational waves to kind of measure even the Dark Ages and different parts of the evolution of the universe. Do you want to add anything to that?
Well, a fun question is to ask yourself, what time would you want to live in the history of the universe in order to be able to see as much as possible of what happened, like before the CMB was formed? Is there a time in the history of the universe when it would be good to live if you wanted to be a cosmologist?
I mean, before the CMB wouldn't make sense for me. I need the CMB.
So if you can go in your TARDIS, like behind you on the wall, what time in the history of the universe would you want to go to see the most stuff?
That is a question I have actually never thought about. And I don't know for sure. Today we already have a lot of technology that is allowing us to see back in time, and we can see a lot of different things. Whereas if we were to go to one specific point, we would be limited by what we can see. Then, of course, you want to go to a point where there is actually light that we can detect. So going to the Dark Ages wouldn't really help because there's no visible light. Going just before the CMB, the light isn't really traveling freely. It's opaque. You can't see anything. I think the most dramatic time, if we're talking about just going and watching it directly, would be when the first stars turn on. Because you go from having practically no light to suddenly flashes and bursts of energy. So I think that would be pretty cool. But I'm curious to know what your answer to this is.
Yeah, I have no good answer. I feel like this is, like I said, I want gravitational waves from before the CMB was formed. So my answer is I don't care. Maybe to the time in the history of the universe when we have the best gravitational wave detectors.
I feel like you tricked me into thinking about that, and now you're not giving a real answer.
That's my job.
Okay, then we have a question from James saying, basic question. It's not a basic question, it's a good question. Would every cosmological event create a gravitational wave, or are they only created at a certain level of magnitude? As an example, would two planets colliding create gravitational waves? Throwing that one to you.
All right. Every time you move matter and energy around the universe, you create gravitational waves, as long as you do it in a way which is not spherical. So, for example, the Earth orbiting the Sun creates some gravitational waves. I think last time I checked, it's about the same amount of energy radiated as a low energy light bulb, so it's not exactly a big deal. Gravitational waves are really, really weak. So especially if you have, that's why you need to go to very, very extreme systems like pairs of black holes colliding to make enough gravitational waves for us to detect them here on Earth, because they're super, super weak. And that's why you need lasers that are in 4-kilometer long cavities interfering with each other in order to actually see them. So they're very, very difficult to make. They're very, very difficult to detect. So the answer is that everything makes them. Like I said, even the Earth and the Sun makes a little bit, and you make them just moving around, moving your arms around. You're making them, but the amplitude is just so small that you'll never ever have any hope of detecting them, because gravitational waves are just such a weak phenomenon, which is, like I said, why we need look at strong things, and we need big detectors. So it's not a basic question. It's a good question. And two planets colliding would definitely produce gravitational waves. And yeah, there's no minimum magnitude at which they're created, except potentially if you're a believer in quantum gravity, then perhaps there is a kind of, one graviton worth would be kind of like the level which it gets difficult to say. But that's a related question. Like, gravity is such a weak force that the energy scale at which gravity becomes quantum, if it ever does, is so high that you'll never be able to see that. As opposed to for photons, where you can count individual photons if you have a good enough detector, or if you're you can. Some people would argue also that in low enough light conditions, your eye can detect individual photons. You can do some kind of algebra to prove that it probably can. You can't see the individual flashes, but over time your retina can build an image from individual photons. So photons are quite easy to do that with. Gravitational waves are much harder to do that with.
Yeah, I like that you gave the example of waving your arms around, because when I'm asked that question, I normally do the experiment of just like spinning on my chair, waving my arms and saying, look, I'm making gravitational waves, but you're never going to measure them. And just to put it in perspective a bit about what a small change a gravitational wave produces. If you have a gravitational wave like the ones LIGO and Virgo have measured, so two black holes smashed together 1.5 billion light years away, it's in ripples throughout the universe. By the time they reach us, this tiny gravitational wave, if it went through you, it would change your height by 1/1000th the width of a human hair, which is a ridiculously small amount. And it's still incredible to me that we can measure such a tiny difference in length. And the ones we're hoping to measure with LISA would be orders of magnitude smaller than that. So it's really something that smaller or bigger.
I mean, do you mean amplitude-wise?
Yeah, amplitude-wise.
I think amplitude is about the strain. If you look at the strain sensitivity of, the way we describe gravitational waves, we use a thing called strain. And when we talk about strain, we talk about exactly the same sort of strain as if, like with elastic band. Here I've got all these props I need, right? So when I stretch this elastic band, it changes its length from its natural length. There we go, that way. And this is, I'm putting a strain on it, right? Or if you bend dodgy bridge's deck, like you're straining the bridge deck or whatever. Like basically, strain is a change in length with respect to natural length of a thing. And so when we measure gravitational waves, we're measuring a strain in space-time, the change of the length in space-time relative to its natural length. And I think the strain sensitivity of things like LISA is actually comparable to LIGO. So the amplitude, like the change in length of things, is about the same for LIGO as is for LISA.
What changes is the wavelength and the frequency.
Yes.
Yes, but the strain is the same. Yeah, so then I can use the same analogy that we're measuring like a billionth the width of a human hair difference with space lasers.
Yes. Yeah.
Which is cool. So I think this question is a good segue into the other main topic I wanted to kind of approach. I know we've gone through a lot of things already. So we talked about what can produce gravitational waves, planets colliding and things like that. So I want to go back to the first picosecond of the universe and what there could actually produce these gravitational waves that we're hoping to measure someday.
Well, lots of things, but the thing that I have a vested interest in is if the universe underwent what's called a phase transition. So if you think about water freezing or condensing into clouds, I would love there to be some water clouds out there. It's been very hot here recently. But yes, so when water vapor condenses into water, or when water freezes into ice, it undergoes a phase transition. So it changes the phase. It's a transition in the phase, like the water phase to the ice phase, and so on. And we think that the universe might have undergone similar phase transitions, like not kind of in terms of materials, but instead the particles, like the fields which make up the universe, might have undergone such phase transitions way back, like these first picoseconds after the Big Bang. We don't have any evidence for it going through any phase transitions at the moment, but we also think that some of the problems that I said I have and other people have with the standard model could be solved if it did go through some sort of phase transition at or above the kind of scale at which the Higgs boson is turning on. And at the moment, actually, looks, if you kind of play through the history of the universe, it's almost like it manages to just avoid going through phase transitions at many different energy scales, which is a bit suspicious as well. So it's a bit funny that it does that. But I think it would solve a lot of problems, kind of theoretical problems, and that we have with the universe if it were to experience phase transitions at or above the kind of scale at which the Higgs boson itself turns on, which is by scale of that scale, I mean the temperature and the time in the universe, which was happening about a few picoseconds after the Big Bang, and energy-wise, a little bit more than what the LHC can manage, like a factor of 10 more than that kind of thing. If we're just going to talk about energy scales or time scales there, so a bit out of reach of us here on Earth, and probably always will be, except maybe indirect hints of things. Like we had hints that we could see the Higgs boson. We knew where to look for the Higgs boson already with the previous generation of particle accelerators, because he said kind of like, look here, and then the LHC kind of knew where to look. So you can see hints of stuff with particle accelerators, even if you can't reach the energy scales where you can directly see the thing you're looking for. But I don't think we're going to be able to see anything much higher energy or mass than the Higgs boson, even with future detectors, because it just becomes prohibitive. But yeah, I think. I digressed. But yes.
So yeah, I want to follow up on potentially three things you said there, and then go back to the other questions. You've mentioned the Higgs boson, and you've mentioned the Higgs boson turning on. So can we maybe just have a brief introduction to what is the Higgs boson, and what do you mean when you say it turns on?
So the Higgs is one of the main things which gives rise to the kind of mass of particles. So it's not the only reason why particles have mass, but the fact that it exists and is there, it contributes a lot of the mass, and kind of it's basically like we talk about these. It's a boson, but it's a boson in the same sense of like photons are a boson. It's a thing which corresponds to a field, and that field is everywhere. Like electromagnetic light radiation is everywhere. The Higgs field is everywhere. And when you pass through it, when other particles, so the electrons and protons and neutrons that make up the atoms in our bodies, pass through it, those particles, not the subatomic particles, the quarks inside the protons and neutrons, they kind of feel slowed down, or kind of experience, not slowed down, but they kind of feel the kind of extra heaviness of having to deal with moving through the Higgs field in some sense. And so that gives them extra mass. So the Higgs is responsible for the mass, like the partially for the mass of these particles. And we think also that the way it turned on may have something to do with why there's in the universe that we see, like here on Earth, but also elsewhere, we only see matter, we don't see antimatter, and that's called the baryon asymmetry of the universe, because protons, neutrons, things called baryons, we don't see any antibaryons at all in the copious amounts in the antimatter at all in the nearby universe, and there's no good explanation for that yet. But many people think that how the Higgs boson turned on might have something to do with that.
Nice. One analogy that I like to think about when we talk about things traveling through the Higgs field is to imagine that the Higgs field is kind of made of treacle or like maple syrup, and you have to get through it, and it's quite difficult. It slows you down. So I like to imagine the early universe filled with like treacle, but that's just because I like thinking about sweet things everywhere. But yeah, the Higgs boson gives everything mass. Sorry,
it's just another field, right? So we've already talked about two fields today. We've talked about the electromagnetic fields, so like electrical and magnetic fields, which are combined into a single electromagnetic field, and we've talked about the gravitational field. And the Earth's gravitational waves, these are everywhere, and they all kind of pervade everything. And the Higgs boson is not it's not a kind of thing which you can just hold on to and like it sits around. It's everywhere. Like the like I said, it's like treacle being everywhere, which is a secret treacle. It's only the quarks and leptons in your atoms can feel. But yeah,
They're hiding it from us.
yeah.
So there's a lot of fun things you've mentioned that we could go off on topics on. Like you mentioned quantum gravity just now, and I decided we're not going down that tangent. So there's a lot of other things of like problems with the standard model that we could discuss, but you already mentioned the main ones, like the lack of symmetry between matter and antimatter. And given that we are already 45 minutes into this, I do want to bring us back to phase transitions. So you mentioned that it's kind of like water changing phase. So what would actually happen in the early universe if we had a phase transition?
Well, depends. If we're talking a phase transition like what water goes through when it condenses or when it freezes, then you would there's if you do it on Earth, then you just water freezes into ice, and it usually nucleates around little bits of impurities in the water or what have you. In the early universe, there's no impurities, at least none that we've kind of like. There's no like dust or other crap there. So what happens instead is that the new phase, the low temperature phase, they go into the ice or the condensed water. This new phase comes into existence either through quantum tunneling, so you tunnel from the old phase to the new phase, or you have some thermal fluctuations that kind of take you over the barrier and get you into the new phase. And that's kind of similar to like you might see if you look on YouTube, you can see like these people who've like left a bottle of water very still on the dashboard of their car, and they hit it and it all freezes suddenly because the water is super cooled. Or you put water in the microwave and you very carefully remove it and you touch it with a spoon and it fizzes over, and that's because it's superheated. Basically, that's the reason why these things happen, is because there's no fluctuations bringing it over to the new phase. So when you touch the water which has been in the microwave, it fizzes over because it's gone above the boiling point of the water. When you touch it, you introduce some sort of perturbation which causes it to fizz over. But in the early universe, there's all sorts of stuff going on, which means that it'll never sit there long enough. So eventually it'll just fizz over of its own accord and end up in the new phase. Whatever happens, you have to get over the barrier to the new phase, this kind of energy barrier. And that's either through quantum tunneling or through like some sort of thermal fluctuation taking you over the top. And when you do that, you'll get a bubble of the new phase, and that bubble will expand. And elsewhere, similar things will be happening with other bubbles, and they'll all collide. And when they collide, they'll make gravitational waves.
So I think that's a perfect chance to bring up an amazing simulation that is super cool. I'm just going to leave it playing. Should bring it on. No. That's the format I want. Okay, so can you tell us what we're seeing here? Well, once I get it in the correct format. There we go. Can you tell us what we're seeing here, what the simulation is?
Okay, so this is a visualization that I did of some simulations we did a while ago. The hotter the color, the more energy there is. And this is actually this is the energy around a bubble wall. So these bubbles are expanding in the kind of soupy, hot, very, very hot soup of the early universe. And they're heating up the rings of stuff as the bubbles expand. They're heating up a ring around the bubbles until the bubbles collide. And we're looking at a slice through a 3D simulation. So you see stuff coming into the kind of the plane of this movie as time goes by, which is why stuff kind of appears to pop into the middle of these bubbles. But what you're seeing the heated rings of stuff, heated rings of plasma around bubble walls. So we're not actually seeing the bubbles themselves, but we're seeing the echoes of them, the kind of fingerprints of them as they heat up the plasma, and then they collide. And then after they're done colliding, we can watch it again, I guess. So here you see these are the rings of hot plasma around the bubbles as the bubble expands in the early universe, as it pulls more and more of the universe into the new phase, the new cooler phase. It expands and it heats up some universe around it, and these bits collide. Like there, you're seeing some collisions there. And when they collide, they produce gravitational waves. But not only when they collide do they produce gravitational waves, but also this heated up plasma keeps going as sound waves. So it's basically a region of higher pressure propagating outwards, and that's basically a pressure wave, and pressure waves are sound waves. So these are sound waves which themselves, as they intersect with each other, produce gravitational waves. So this is one of the main ways in which we would expect to see gravitational waves produced from a first order phase transition. If we were to see one, this sort of process you're seeing here would probably be the way in which we would. This is the what you're seeing happening here is what would source the gravitational waves that we would detect from that, if we detect it. And if we don't, like I said, that's fine with me as well.
So I really like the simulation or the animation that you have here, and I know it's been used in a lot of places. Just to clarify something, you said the hotter colors are more energy. By hotter colors, you mean the redder ones?
So when I made this, this visualization, I wasn't really thoughtful about colorblind accessible color choices or actually what worked. So yes, I mean redder. I would probably in retrospect not have used this color choice. We have to live with our decisions. These movies are everywhere now, so I can't really go back on it. But yes, more red, more of those colors, reds.
I just took it off just as you were pointing to the bookshelf. Wrong way around. That's better. Yeah, I wanted to clarify that because obviously, if we see a lit flame, then blue is hotter. So it's always ambiguous when we refer to a hot color or cold color. But it is a very cool simulation, and it's one that, as you say, has been used a lot. And I think it's really nice that we can actually do these simulations of what a phase transition would look like, and from there going to gravitational waves. So what goes into making this type of simulation?
So the simulation just watched is a hydrodynamic simulation. So it's not that different from kind of weather forecasting simulation, because they both involve simulating what fluids are doing or might do. But in this case, this is a hydrodynamic simulation in the early universe, and it has to take into account at least special relativity, so things can get close to the speed of light, but not general relativity, because there's nothing here which is so dense that space-time can be curved per se. So this is a relativistic hydrodynamical simulation. So it's the behavior of fluids moving potentially close to the speed of light. And you, in this case, in the simulation you just saw, that was a small slice through an example of one of the simulations we did for a paper, where the biggest simulations took about they took over 1 million computer hours to complete, and used on the simulation itself ran on about 42,000 CPU cores, simultaneously for about 24 hours. So that was done at the HLRS Center in Stuttgart in Germany. And so typically you need tens of thousands for the largest sizes here that we were able to access, tens of thousands of CPU cores, and you need to run for several hours to get this sort of thing. I'm not proud of the energy utilization of these. This does not bring my carbon footprint down by any means, if you blame me for these simulations. But so I do try to keep them to a minimum, and in some sense I'm hoping that by kind of doing these simulations you kind of make them obsolete, right? So if you simulate the right things enough, then you can understand the theoretical underpinnings of them, and then it's no longer my problem. I can go off and do something else, because like I said, I do computer stuff. I don't do like blackboards and things, and so they become someone else's problem once we understand the theoretical underpinnings well enough that we don't need computer simulations. And that's my goal. My goal is to make myself obsolete.
Yeah, so just to clarify that, to elaborate on that, you run the simulations, and from there you can then extract analytical approximations that you can use to not need to run them again, right?
Hopefully.
So ideally, we use the results from previous simulations, and then we don't need to redo them each time.
Yeah, I mean, there's so many different things that you would kind of want to, like I said, particle physics phenomenologists will create enough theories, more theories than you could ever test kind of end to end all the details of. So what you eventually want to do is basically understand, as with any science, you want to understand the underlying general principles and be able to refine them and extract them without having to kind of put things into the black box of the simulation every time. And I think it would be unscientific to need to do simulation every time. The reason why we need to do simulations of the weather, for example, is that the weather is a very sensitive system to initial conditions. So we do need to simulate the weather. We can't just say, well, red sky at night, shepherd's delight, red sky at morning, shepherd's warning. We do need to do simulations to understand what's going on. Whereas for the early universe, we do want to try and infer general principles which apply more generally than just like, oh yes, we do a simulation for this different thing.
You just threw me off with the random farmers quotes there.
Oh, I mean, it's like you don't, you can't, sometimes there's a red sky at night, but sometimes it's just, sometimes it's because the neighboring village is being burned. Who knows? It's not necessarily a physical principle underlying the weather that the red sky at night means that the shepherds will be happy in the morning. It could also be the shepherds could be depressed. You never know. Yeah.
It's a fun tangent to go down, but no, we're always happy for tangents on the show. So I think these simulations are really cool because they really show us both what's happening in the early universe and they show us the gravitational waves that we might detect one day with LISA. So it really allows us like an end-to-end map of how we go from this early universe physics to what we might measure by sending lasers to space, which is ridiculously cool. So is there anything else you want to tell us about phase transitions or gravitational waves before we move into a slightly different topic?
I think I'm good. If anyone has any questions, they can ask in the chat or send me an email or find me on Twitter afterwards or whatever they want to do. But yeah, I'm happy to move on if you are.
Okay, so I'm going to go back to a question that we have from James. James raised it as a completely off-topic question. So we stated that we're co-workers. James is wondering, is it team research? Is everyone independent? Do we have projects, objectives, management, deliverables? How does the group work? And I want to throw that question over to you.
All right. Yeah, thank you for the question. It's a good question. So yeah, how do I answer this? It's a good question. So I have funding and from various pots of money, and one of those pots of money pays Diana's salary, but I don't consider Diana to be in any way answerable to me. I hope that Diana does whatever they choose to do, as long as it's scientific and it is vaguely related to what the project is meant to be about. I think in our group, and we, to the best extent possible, we try to avoid having very clear like lines of hierarchy or kind of power, and people, for example, always have multiple supervisors. So I think it's very important to me that we have multiple more senior people working with multiple less senior people, whether that be kind of faculty with PhD students and postdocs, or if it's or with summer students and master students. There should always be multiple more senior people around because it reduces the risk for kind of abuse of power. It also means there's more people around if somebody's off sick or on vacation, and it also just makes for a more interesting kind of constructive friction when more people are talking about projects. So Diana and I are co-workers. We're both answerable to the people who fund us. And that in large part is the Academy of Finland, which is a national funding body here that does peer review on grants and then gives us money to do the research that we're doing. And then we're answerable to them because at the end of the day we have to write papers and explain what we did with the money and how we used it. And if we do use it for travel or for equipment, we have to justify that separately. And they won't give us any more funding, and they'll take away our funding if the reports that we write don't adequately justify that we've made progress or done what we said we're going to do. Of course, not making progress is also fine, but usually find out interesting things anyway, even if you don't make progress, and that's okay. So it's okay to not make progress. Sometimes things are just difficult. So it's at least the way I conceive of it, and again, this is not just me working in a vacuum. There's lots of other cool faculty that we work with here. That I'm not doing this on my own, and Diana's not doing it on their own either. We definitely conceive of these projects generally as working in a team, and we're answerable to our funders. There is line management, so I have a boss, and actually I think my boss is also technically Diana's boss because of the way the kind of human resources system works here. And then it goes all the way up to like the head of the department and the dean and the rector and stuff. So there is a line of responsibility there, but in terms of the research we do, we're answerable to our funders. And so that is how I would answer that question. Does that cover it, do you think, Diana?
I think that's a good answer to the question. and we managed not to rant too much, so that's good. But yeah, I think it's a great question. It's also good to demystify the whole scientific process. And I do want to add to the final part there of, do we have deliverables? Now, usually when you write a grant, which I'm unfortunately way too familiar with currently, you make a list of objectives and you promise deliverables. But research constantly changes. Sometimes you go in one direction, sometimes you go in another. There's always unexpected things happening. So you might promise, like, I'm going to write this many papers, I'm going to deliver this many things. It may or may not happen. You might write more, you might write less, you might have a problem, and this is fine. At some point, you do have to write a report saying this is what I spent the money on. But otherwise, it is flexible. And we don't have clear deadlines like, I need to do this paper today because this is what I promised the funding agency. Science is constantly changing and you adjust to that. And as long as you don't work on something completely different to what they gave you money to, most of the time they're happy with you. And sometimes it is even like, yeah, just go do whatever you want. That's fine. As long as you can somehow justify it, people are happy with it. So we are already at 1 hour. So I want to finish by asking you a question that I think is very interesting. So one of the objectives behind Cup of Cosmology is to demystify scientists and to demystify this idea of the lone genius scientist, which we're already just covering right now. So yeah, I never promised to find dark matter, Scott. I said, like, I will look for dark matter. I never promised to find dark matter. So the last question I'd like to wrap up on is, what is your favorite part of being a scientist?
Well, it comes back to just what we've been talking about, doesn't it? So I really enjoy the fact that we get to solve problems as part of a team and we do things together, and it's very enjoyable. I mean, I think that's an experience you can have anywhere. You don't have to be a scientist to do it. You can work in industry. And I think there's nothing, as you said, we want to demystify what academia is like and what being a scientist is like. And there's nothing, it's basically at the end of the day, it's problem solving in a team. And that's something which happens across a wide range of ways of life, sectors, businesses, group activities, hobbies. You're solving problems together. And that's the fun part, is that you work with cool people, you learn interesting things, and you find out something new. And that, to me, is the best part of it. I don't think it's about trying to be a genius or going off discovering something really amazing, because realistically, the chances of me doing that myself or us doing that together are very, very small. So the main thing is to learn cool things and have fun.
Yeah, I love that answer. So a couple of weeks ago, I did a stream about my favorite thing of being a scientist, and it was basically 1 hour to say exactly what you just said in 2 minutes. But yeah, the science is cool, but talking about science with people is more fun than doing the actual science. It's why I really like having coffee breaks where we can just bounce ideas back and forth, journal clubs where we can discuss things informally, which is a reminder that I'm supposed to prepare a journal club for tomorrow. But it's nice to just have these like informal discussions and really just talk about these amazing things, not just among scientists, but to everyone. And that's what Cup of Cosmology is here for, to talk science at people. I would say you can't run away, but you can just literally turn us off if we bore you. But that is what we're here for, to chat science. Okay, so we have passed the hour mark. Is there anything else you want to tell us, want to let us know about, or think people should take away before we wrap up?
No, I think it's good. Like I said, I'm very happy to answer any more questions people have if they want to reach out on Twitter or drop me an email or something. I'm always happy to talk, and thank you very much for the invitation to appear on your stream. It's been great.
Thanks for joining. It's been really fun to have you online. So Cup of Cosmology will be back online next Sunday, same time as today. That is 8 p.m. Helsinki time, 7 p.m. the rest of Europe, or most of Europe, 1 p.m. Eastern Standard Time, 10 a.m. West Coast. I've finally learned all of the time zones by memory, so there's a time zone converter on Cup of Cosmology, so you can put it in your own time zone. And next week, we will actually be celebrating the 7-year anniversary of Cup of Cosmology, which is ridiculous to think that I've been doing this for 7 years now, but I should be online next week. If you haven't done so already, please like the stream, leave a comment, subscribe, press all the buttons, follow David on Twitter. You can find that from my Twitter very easily. And yeah, I will be back. And David, if you ever want to come back, you are welcome back as well. But I will be back online next week. And I hope in the meantime, you all stay safe and take care of each other.